Welcome. In this short video lecture, we are going to discuss about ordinary and regular points of a differential equation. I hope it will be useful to you. So before we define the ordinary and singular points, we need to define what we mean by a function being analytic at a point x naught. So definition, we say a function f of x is said to be analytic at a point x naught if it is convergent or it has a convergent series on an open interval about the point x naught. So this is the definition of analytic function at a point x naught. Or simply we can say a function f of x is called analytic at x equals to x naught if f of x is equal to its power series. I remember at all analytic points of a function, then the function can be differentiated at those points. So therefore now let's start by defining what we mean by an ordinary point and a singular point. So definition, ordinary and singular points. So I'll give the definition based on a second order differential equation. So we say the point x naught x equals to x naught is an ordinary point of the differential equation capital P of x d squared y dx squared plus capital Q of x dy dx plus capital R of x y equals to 0 if we define small p of x as the ratio of capital Q of x divided by p capital P of x, and we define small q of x to be the same as capital R of x over capital P of x, are analytic at x naught. Otherwise, the point x naught is a singular point. So this is what you're saying, that if you have this second order differential equation, capital Q of x y double prime plus capital Q of x y prime plus r of x y equals to 0. So we can rewrite this differential equation in the form, when you divide through by capital P, then d squared y dx squared plus small p of x dy dx plus small q of x y equals to 0, or the same thing as saying y double prime plus small p of x y prime plus q of xy equals to 0. Then if p small p of x and small q of x are both analytic at x naught, then that point is called an ordinary point. But if either p small p of x or small q of x, none of them are analytic at x naught, then that point is called a singular point. So we can say from this definition that thus, if p capital Q and capital R are polynomials, so now that we are saying that are polynomials, so this is a special case of functions having no common factors, then the singular points of the differential equation, let's call this differential equation 1, of the differential equation 1 are the points for which capital P of x equals to 0. So remember, the key thing here is that if P, Q, and R are polynomials, not just any other kind of function by polynomial, this now when you say that you get singular points by letting capital P to be 0. But if they are not polynomials, then that's not the, that might not be the case. So examples. So one, just test whether or show whether the point x equals to 0 is an ordinary or singular point to the differential equations x y double prime plus sine of x y prime plus x squared y equals to 0. So here now, this is how we show this. Solution. First, observe that capital P of x is small x, capital Q of x is sine x, and capital R of x is given by x squared. So it turns out that small p of x will be given by small p of x will be given by capital P, a capital Q over P, which will be given by sine x over x, and then small q of x will be given by r over p, which is, remember this is x squared, so x squared over x, which will be x. So then now, so we have to show whether, so we need to show that, whether both small p of x and q of x are analytic at x equals to 0. So then observe that this small p of x is given by sine x over x, and then sine, this can be written as 1 over x times sine of x, and then this is the same as 1 over x into sine can be written as a series x minus x cubed over 3 factorial plus x power 5 over 5 factorial minus x power 7 over 7 factorial plus etc. And then when you multiply by 1 over x, this will give us a small p of x equals to 1 minus x squared over 3 factorial plus x power 4 over 5 factorial minus x power 6 over 7 factorial plus etc. And then it is very easy to see that if this function here is convergent, which is convergent for all values of x. Thus, this means that p of x, thus both p of x, or this convergent, then it means that we can have a power series about the point x equals to 0. So which means that the function p of x is analytic. So both p of x and q of x are analytic. So if they are analytic, then this shows that the differential equation, the given equation is has an ordinary point about x equals to 0. So therefore, x equals to 0 is an ordinary point. Of the given differential equation, because it agrees with the definition of an ordinary point. And then number 2, the Bessel equation of order V are given by x squared y double prime plus x y prime plus x squared minus b squared y equals to 0 has an ordinary point, has a singular point, not an ordinary point, has a singular point x equals to 0, since in this case, capital P of x equals to x squared, and then q of x equals to x, and capital R of x equals to x squared minus v squared. So all these p, q, and r, all of them are polynomials. P, q, and r both all of them are polynomials. And then if we go by the definition of a singular point or an ordinary point, if P, Q, and R are polynomials, then if we set capital P of x equals to x squared equals to 0, then this tells us that x equals to 0 is or a singular point of that given differential equation. So, and what actually another way of doing it is just saying that small p of x is given by x over x squared, which is 1 over x, and q of x will be given by x squared minus v squared over x squared. Though this will give us 1 minus, so this will give us 1 minus v squared over x squared. Clearly, you see that this small p of x, this function cannot be differentiated at the point where x equals to 0, similar to this other part here. So both p of x and q of x are not differentiable at x equals to 0. So which means that both are not analytic at x equals to 0, and that means that the point x equals to 0 is a singular point. And then any other point, just to note, any other point apart from the point x equals to 0 is an ordinary point, meaning that the given all those points apart from x equals to 0 are analytic for the given values of small p of x and q of x, ordinary points. And then example 3, the Legendre equation (1 minus x squared y double prime minus 2x y prime plus alpha into alpha plus 1 y equals to 0. Since this is a polynomial, this also a polynomial, and this is also a constant polynomial, then 1 minus x squared, which is our p of x, if we equate it to 0, it will give us x squared equals to 1, which means x equals to plus or minus 1 are singular points. Singular points, and any other points apart from x equals to 1 and x equals to -1 are ordinary points. But note that we are doing this when we're taking capital P of x and equating to 0 and solving to get the ordinary, to get the singular points, because capital P of x, capital Q of x, and capital R of x are polynomials. If they are not polynomials, then you have actually to find the small p of x and small q of x and try to manipulate them the way we have done in question 1 to be able to know whether those points are singular points or ordinary points. So we only equate capital P of x, not that one. Don't forget that one, because if you forget that one, then you might get some wrong answers to some questions. We only equate this to 0 to find singular points of a differential equation if this P of x, Q of x, and R of x, all of them are polynomials. But if none of them are not polynomials, then you have to define the small p of x and small q of x, and actually try to test whether this quotient and this quotient are either analytic or non-analytic at that point specified for you to be able to give the conclusion. But don't just hurry to take capital P of X and equate to 0 and then say that I have this singular point. That will only be done if you have confirmed that P, Q, and R are all polynomials. So let's define what we mean by regular singular points. So we also consider the same equation given in 1. So we say that given a second order differential equation, capital P of X, Y prime, Y double prime, plus capital Q of X, Y prime, plus capital R of X, Y equals to 0. Then let me just call this one 2. 2 is 2 has a regular singular point about or at X equals to X naught if X minus X naught multiplied by this ratio, capital Q over capital P, and X minus X naught squared times capital R of X divided by P of X are both analytic at the point X equals to X naught. So that is the definition of a point X equals to X naught being a regular singular point for the second order differential equation given in this by this equation. But for special cases, in case where P, Q, and R are all polynomials, then we say if P of X and Q of X happens to be polynomials, then X equals to X naught is a singular regular point or a regular singular point if these two limits are finite. Limit as X approaches X naught of X minus X naught multiplied by Q of X over capital P of X, and limit as X approaches X naught of X minus X naught squared multiplied by R of X over capital P of X. Both are finite. So finite means that we have when you take the limits of these functions, you get a number. You get a function. It's not infinity. So a quick example. Then just any other point, any other singular point X naught is an irregular singular point. That means that anyone that doesn't obey these two conditions we have given here for the case where P and Q are polynomials, or just using this general definition, if you find that these two functions, this and this one, are not analytic at x equals to x naught, then if that x naught was a singular point, then it is called irregular singular point. So for example, consider, so these are examples. If we have this Bessel function of order V, Bessel differential equation of order V given by this equation, then we can see clearly that the point x equals to 0 is a regular singular point since the following limits are finite. So this is what we mean. So limit as x approaches x naught of x minus x naught q of x over p of x will mean limit as x approaches 0, because that's our x naught that you're referring to, x minus 0, and then q of x is x, and then over p of x is x squared. We see that this would be limit as x approaches 0. This x minus 0 is just x, so x squared over x squared, so which will give us limit as x approaches 0 of 1, which is 1. So that is finite. And then limit as x approaches x naught of x minus x naught squared r of x over p of x will be the same as limit as x approaches 0, and then x minus 0 squared, and then x squared minus v squared divided by x squared. And then this will give us limit as x approaches 0 of x squared into x squared minus v squared over x squared. So this and this cancels out, so that we have limit as x approaches 0 of x squared minus v squared, which will give us minus v squared. So this is still a number. So therefore, that's a confirmation that the point x equals to 0 is a regular singular point for that given Bessel differential equation. Similarly, if we have the Legendre polynomial equation given by this, and then plus alpha into alpha plus 1y equals to 0, the point x equals to 1, the points x equals to 1 and x equals to minus 1 are also regular singular points. Now we can demonstrate for the point x equals to 1 to show that one. So we just need limit as x approaches x naught of x minus x naught q of x over capital P of x. This will be limit as x approaches 1 of x minus 1. Our p of x is minus 2x. You can see here, p of x is minus 2x divided by, this is our 1 minus x squared. And then this is the same as limit as x approaches 1, x minus 1, and then times, I can say minus, and then minus 2, and then x over 1 minus x, 1 plus x. This is a difference of two squares. So this is the limit as x approaches 1. Can bring this negative inside so that I have 2x into now 1 minus x over 1 minus x, 1 plus x, so that these two brackets cancels out. So this bracket cancels out, and then I will get limit as x approaches 1 of 2x over 1 plus x, and direct substitution will give us 2 times 1 over 1 plus 1, which is give us 2 over 2, which is 1. So this is a finite value. And limit as x approaches x naught, x minus x naught squared r of x divided by p of x will be limit as x approaches 1 of x minus 1 squared, and then multiplied by, that's r of x is alpha plus 1, and then divided by p. So p, which is 1 minus x squared. So this will be limit as x approaches 1 of x minus 1, and then and say x minus 1, and then alpha into alpha plus 1 divided by 1 minus x, 1 plus x, and then this is the same as actually this can be written as, I can factor out negative here. So I have limit x approaches 1. I say negative 1 minus x, and then also this other I say negative 1 minus x. So there's nothing I've changed. I've just written this one in the by factoring out negative so that I start with 1, and then I have alpha plus 1. I divide this one by 1 minus x, 1 plus x. So that will give me limit as x approaches 1. So negative cancels out so that I have 1 minus x, 1 minus x, and then alpha plus 1 over 1 minus x, 1 plus x. And then we see clearly that this now will cancel out, so that now when we have limit as x approaches 1 of 1 minus x into alpha plus 1 divided by 1 plus x, and when you do direct substitution, you have 1 minus 1 into alpha plus 1 divided by 1 plus 1, which will give us 0. So therefore, this is a finite value, and that's a confirmation that x equals to 1 is a regular singular point. You can actually similarly do for the case x equals to -1 and confirm that both the limits will give you finite values. So that's how we find ordinary singular points and regular singular points. So thank you.